Good morning, everyone. Welcome to today's presentation. I am delighted to have you all here. Today, we will be exploring the topic of calculations of chemical analysis. My name is Dr. S.K. Singh, and I hold a Ph.D. in this field. In this session, we will cover key concepts and methods involved in chemical analysis calculations. We'll look at some practical examples and discuss how these calculations are essential in our work. So, let's get started and dive into the fascinating world of chemical analysis. Chemical analysis is a fascinating area within chemistry that focuses on understanding the composition of substances. It involves identifying what chemical components are present in a sample and how much of each one there is. When we talk about chemical analysis, we're essentially trying to get a detailed picture of a sample's makeup. This can be done through two main approaches: qualitative analysis, which tells us what substances are in the sample, and quantitative analysis, which measures the amounts of those substances. To achieve this, scientists use a variety of methods, including chemical reactions, instrumental techniques, and physical measurements. Overall, chemical analysis is crucial because it helps us understand materials better, whether in research, industry, or quality control. It's a key part of the broader field of chemistry that ties into many applications across science and technology. To prepare a 0.1 molar sodium hydroxide solution, we start by dissolving 2 grams of sodium hydroxide pellets in 250 milliliters of distilled water. Once the pellets are fully dissolved, we then make up the total volume to 500 milliliters. This ensures the concentration is accurate and consistent. Now, when we talk about molarity, especially in the context of the Indian pharmacopoeia, it's important to note that all solutions are expressed in molarity. Molarity, or M, is simply the number of moles of solute, meaning the substance being dissolved, per liter of solution. The solute is the substance that we're dissolving, like the sodium hydroxide in this case, and the solvent is usually water, the substance in which the solute dissolves. Understanding molarity is crucial because it helps us quantify solutions precisely, which is essential for chemical analysis and ensuring reproducibility in our experiments. So, in essence, molarity provides a clear, standardized way to communicate how concentrated a solution is, and that's a key concept in our overall discussion of chemical preparations and analyses. Let's take a closer look at how sulfuric acid solution is prepared. We start by dissolving 49 grams, which is approximately 26.6 milliliters, of sulfuric acid into 250 milliliters of distilled water. Then, we make up the total volume to 1,000 milliliters. This process ensures we have a standardized concentration for our experiments. Now, in the context of acids and bases, you'll notice the term N used frequently. This N represents the number of replaceable hydrogen ions in acids or hydroxide ions in bases. It's a key factor because it helps us quantify the reactive capacity of a solution. Moving on to normality, or N, this is a measure of concentration that tells us the number of equivalents of solute per liter of solution. It's not just about the mass or molarity. It specifically considers how many reactive units, like H+ or O ions, are present in the solution. To determine the equivalent weight, we take the molecular mass of the substance and divide it by the number of replaceable ions or electrons involved in the reaction. This way, normality gives us a more functional measure of a solution's reactive capacity, especially useful in titrations and chemical analysis. Speaking of chemical analysis, understanding these concepts of concentration and equivalent weights is crucial. They allow us to accurately analyze and compare solutions, ensuring precise and reliable results in our experiments. This connection highlights how fundamental these ideas are to our overall goal of understanding chemical reactions and solutions better. Let's discuss the assay of albendazole using acid-base titration. First, we dissolve 0.5 grams of albendazole in 80 milliliters of anhydrous glacial acetic acid. This creates our solution for titration. Next, we titrate this solution with 0.1 molar perchloric acid, and we use crystal violet as our indicator to signal the endpoint. It's important to carry out a blank titration as well, to account for any impurities or background acidity. The key point here is the factor. 1 milliliter of 0.1 molar perchloric acid is equivalent to 0.02653 grams of albendazole, which is C12H15N3O2S. Before proceeding, we need to standardize the perchloric acid solution according to the IP to ensure accuracy. Now, to give a quick overview of titration itself, it's a volumetric analysis method where we use a standard reagent, called the titrant, to determine the concentration of an analyte. We measure how much titrant reacts with our analyte solution, and the volume used is called the titration volume. There are various types of titrations, but the most common in qualitative analysis are acid-base titrations, redox titrations, precipitation titrations, and complexometric titrations. In our case, we're focusing on an acid-base titration to quantify albendazole. This method is fundamental because it allows us to accurately determine the drug's content, ensuring quality and compliance with standards. Let's go through the key points for standardizing our 0.1 m perchloric acid solution. First, we take about 0.35 grams of potassium hydrogen phthalate, or C8H5KO4, which we need to weigh accurately. It's important that this compound has been lightly powdered and dried at 120 degrees Celsius for about 2 hours to ensure consistency. Once prepared, we dissolve this in 50 milliliters of anhydrous glacial acetic acid, which acts as our diluent. Next, we add a small volume, about 0.1 milliliters, of crystal violet solution, our indicator. This indicator will help us identify the endpoint of our titration. Then, we titrate this solution with our perchloric acid until the violet color of the indicator shifts to an emerald green hue, signaling the completion of the titration. Don't forget, we need to perform a blank determination to account for any background color or impurities, and then apply any necessary corrections to our measurements. It's also crucial that our solutions are within the specified strength, meaning they shouldn't differ more than 10% from the prescribed concentration. And for accuracy, we aim to determine the molarity with a precision of about 0.5%. This process ensures our standard solution is precise and reliable, which is fundamental for the accuracy of the entire analytical procedure. Today, I want to introduce you to titrometric analysis, which is a fundamental technique in analytical chemistry. It's essentially a quantitative method that involves the gradual addition of a titrant to a solution until a reaction reaches its endpoint. This endpoint is usually indicated by a color change or some other measurable signal. The key point here is that titrometric analysis allows us to determine the concentration of an unknown solution precisely. It's widely used because of its accuracy and reliability. As we continue through this presentation, you'll see how titrometric methods fit into the bigger picture of analytical techniques and why they remain essential in various applications. Let's talk about titrometric analysis. This is a classic quantitative method used in chemistry to determine the concentration of an unknown solution. The key idea here is that we add a titrant of known concentration gradually to the analyte until the reaction reaches its endpoint. This endpoint is often indicated by a color change, thanks to an indicator. The main concept to remember is that the volume of titrant used is directly related to the amount of analyte present, thanks to the stoichiometry of the reaction. This makes titrometric analysis highly precise and reliable for various applications, from quality control to research. Connecting this to our overall theme, titrometric methods exemplify the importance of quantitative analysis in chemistry. They allow us to measure substances accurately and efficiently, which is fundamental in both industrial and laboratory settings. So, understanding titrometric analysis is essential for mastering chemical quantification techniques. Now, let's take a closer look at the key numbers involved in this calculation. The number 36.04 represents twice the molecular weight of water. Since water's molecular weight is 18.02, multiplying that by 2 gives us 36.04. The number 230.08, on the other hand, is the molecular weight of sodium tartrate dihydrate. These values are crucial because they help us relate the amount of reagent used in the titration to the actual water content in the sample. In this context, W stands for the weight in milligrams of sodium tartrate dihydrate we're using, and V represents the volume in milliliters of the reagent consumed during titration. These two variables are essential because they directly influence our calculation of the water content. Now, moving to the core concept here, Karl-Fischer titration is a powerful method for measuring water content across a wide range of substances. Its beauty lies in its specificity and accuracy. To ensure our measurements are reliable, we need to standardize the KF reagent, and we do that using disodium tartrate. The key to this standardization is the water equivalence factor. Denoted as F, this factor tells us how many milligrams of water are equivalent to 1 milliliter of the reagent. The formula for F incorporates these molecular weights and the weights of the substances involved, providing a precise way to relate reagent consumption to water content. In summary, understanding these constants and how they fit into the formula is fundamental for accurate water determination using Karl-Fischer titration. It ties together the chemical properties with the analytical process, ensuring our results are both accurate and reproducible. Now, let's look at Siphacos and its water content. The limit for water in Siphacos is set between 3 and 6.5%, and this measurement is based on a 0.2 gram sample. This range is important because it helps ensure the drug's stability and efficacy. To determine the water content, we use a method called Karl-Fischer titration, which is highly precise and widely accepted for moisture analysis. This technique involves reacting the water in the sample with a reagent, allowing us to accurately quantify the water present. Understanding and controlling water content is crucial in pharmaceutical quality control, as excess moisture can affect the drug's performance and shelf life. So, by applying Karl-Fischer titration, we can reliably monitor and maintain the proper water levels in Siphacos, ensuring it meets the required standards. Let's start with an important note about the drying and ignition process. After drying or igniting a sample, we need to weigh it twice consecutively. The key point here is that these two weights should not differ by more than 0.5 milligrams. This ensures that the measurement is stable and accurate before we proceed. Now, focusing on levosalbutamol sulfate, specifically the loss on drying test, which is identified as test 2419. The maximum allowable loss on drying is 2%, and this is determined by testing a 1 gram sample at 105 degrees Celsius. So, what exactly is loss on drying? Essentially, it's the percentage of weight lost due to water or other volatile substances that can be driven off under specified conditions. This is an important quality parameter because it reflects the presence of residual moisture or volatile impurities in the sample. Understanding and controlling loss on drying helps ensure the stability and consistency of the pharmaceutical product. It's a key part of quality control that guarantees the product meets its specifications and performs as expected. Let's talk about the drying and ignition process. It's important that we dry or ignite the sample until it reaches a constant weight. This means that after 2 consecutive weighings, the weight shouldn't differ by more than 0.5 milligrams. This ensures that all moisture or volatile substances have been properly removed, giving us accurate results. Moving on to levosalbutamol sulfate, the limit for sulfated ash is set at no more than 0.1%. This is a key quality parameter because it indicates the amount of inorganic residue left after the sample is ignited. The sulfated ash test itself involves heating the sample in the presence of sulfuric acid. This process helps us measure the residual inorganic material that doesn't volatilize during ignition. It's particularly useful for identifying inorganic impurities in an organic compound. So, by controlling these parameters, we ensure the purity and consistency of our pharmaceutical product, which is essential for both safety and efficacy. For further support, please don't hesitate to reach out. If you have any questions or need clarification, we're here to help. Remember, we're committed to ensuring you feel confident with this material. So feel free to contact us at any time. Thank you very much for your attention and engagement today. We appreciate your time and participation.